So let's now see the graphical representation of the complex numbers. Okay, so since complex numbers are constructed from pairs of real numbers, it is natural, to represent complex numbers graphically as points in a Cartesian plane, right? Because obviously complex numbers you are constructing it from pairs of real numbers. Okay, x plus iy, where x and y are real numbers. Okay, so then it is, natural to represent them in a graphical way. So now what we do is points with coordinates a comma b represent complex number present a complex number a plus ib, a plus ib. This is how the coordinate will represent. Okay, so obviously 1 comma 0 will represent 1 plus 0 I, which is 1. Okay, similarly your 0 comma 1 will represent the imaginary unit I. So let me just draw it. So here you will have the 0 comma 0 will be here, somewhere here it will be 1, and similarly 2. Okay, and here it will be I, and after, if you just extend it, it will be 2i, 3i, something like that. And this will be basically 1 plus I. This coordinate, this point will represent 1 plus I. This will represent 2 plus I. Okay, and similarly say the point minus 2 will be somewhere here, and here you will have minus 2i. So this point will be somewhere 2 minus 2i. Okay, so this is called the real axis, this is called the imaginary axis. And why imaginary axis? The number that is attached to the imaginary I here, say for example 2 plus I, okay, will basically represent 2 comma 1. Okay, 2 comma 1. Similarly only the imaginary numbers, the numbers that are attached to the I part, so will have will lie only on the imaginary axis. So so the points which lie on the imaginary axis will have only the imaginary part. That's why the points, all these points together which lie on this axis will have only the imaginary part. Okay, and that's why it's called imaginary axis. So this is how, just a simple representation of complex number. And such a representation is of complex number by taking points in a plane is called Argand plane, Argand diagram. So points on x-axis corresponds to real numbers x plus 0 I. Okay, and that is real axis. And points on y-axis corresponds to pure imaginary numbers, or the complex numbers which have only the imaginary part. So something like iy is basically 0 plus I into y. Okay, so that's why all that the entire axis is called imaginary axis. Okay, so this is what we get from the graphical representation. Now other things which you can make out is the distance from origin to the point x comma y basically represents corresponding to a complex number. So x comma y basically corresponds to a complex number x plus iy. Okay, z, let's say z is equal to x plus iy. So this distance from the origin to this x comma y, which represents complex number x plus iy, is called the modulus of z and is denoted by mod z, which is nothing but mod x plus iy, and that represents the distance from origin to the. So this is how the modulus is defined. It is the distance from the origin to the point x comma y, which represents a complex number. So this is about the modulus definition. Now let's discuss what is argument. Okay, so another definition coming up. If the line from origin to x comma y makes angle theta with positive direction of the real axis, so positive angles means measured counterclockwise. Counterclockwise. Okay, measured counterclockwise. Then we call theta as an argument of complex number z is equal to x plus iy. So that's what, uh, and this we denote by argument of z is equal to argument of x plus iy. Okay, and basically is equal to theta. So let me just explain you. Okay, you have something like this. You have, this is the origin. You have some point which represents x plus iy. Now the line joining origin to x comma y, which represents a complex number. So in the counterclockwise direction from the real axis, you have angle theta. So that is nothing but is called as the argument of this complex number. Okay. So now a couple of things. Modulus of a complex number is always real and non-negative because basically it represents distance. Okay, it's always real and non-negative. Whereas, and this modulus basically plays the same role for complex numbers that absolute value function does for real number. So this plays the same role for complex numbers that absolute value does for real numbers. And hence why sometimes modulus is called absolute values. Okay. Now coming to argument. Argument of a complex number is not unique. Now this is something which is, you think why. Now you may have angle theta, okay, and you can actually come in one cycle and then again measure angle theta. So it's something like this. Two possible values basically differ by an integer multiple of 2 pi. I can say this because this same angle, say theta is 30, I can say the argument is 360 plus 30 or 720 plus 30, like that. So argument is not unique because you may have, I mean 30 as well as 390 as well as 750, they are same. Okay, so argument z is equal to argument of a plus iv. So not unique. I mean you can say the two possible values differ by integer multiple of 2 pi. Okay, so I can write this as theta, theta plus 2 pi, theta plus 4 pi, so on. Okay, so in general, argument is theta plus 2k pi, okay, where k belongs to integers. It can be plus or minus, okay. And remember that another important thing is tan of argument of w. Okay, so tan of argument is basically tan of argument is basically angle. That's the thing. A plus IB, and this becomes basically B by A. We can just recall because this tan of angle, this will be basically this distance is y and this distance is x and this distance is y. So I can write tan theta as y by x. So in similar form, I can write tan of argument of A plus IB is basically B by A. Okay. So most of the time we restrict argument in this range. Either theta varies from 0 to 2 pi or we restrict in this way minus pi to pi. Okay, so in order to avoid that multiple things, restrict in this way. Okay, so now let's represent various complex numbers. Okay, so now let's represent various complex numbers and to calculate mod and argument of them. So we have seen what is modulus, we have seen what is argument. Okay, so if you have complex numbers at 2, or if you have 1 plus I and you have I, you have minus 3 plus root I. So let's call the argument. Okay, so mod 2 is 2 and the argument of 2 would be 0 because it lies on the real axis, right? 2 lies somewhere here. So the angle it makes, so this is your argand plane. Okay, then 1 plus I modulus will be root x square plus y square, so root 1 plus 1, 1 square plus 1 square root 2. The argument of 1 plus I will be basically, so 1 is somewhere here, I is somewhere here, so it is somewhere here. So this is 1 plus I, this is 2. Okay, and that angle is nothing but, this angle is nothing but tan of b by a. So tan inverse of b by a, which is tan inverse of 1 by 1, which is 45, right? That's what you can write. Then I modulus will be root 1 square will 1, and then the argument of I will be basically I is somewhere here, right? So this angle is 90. So straight away you can say, or you can find tan inverse 1 by 0, which is not defined, 90. Okay, so similarly root 3 plus I will be root over root 3 whole square plus 1, so it will be root 4 is equal to 2. So this is the modulus. Now argument of minus root 3 plus I will be basically tan inverse of b by a, that is 1 by minus root 3, which is nothing but when you can just recall that 1 is here, I mean minus root 3 somewhere here and 1 is here, so it's somewhere here. This represents minus root 3 plus I, this number. Okay, and so the angle is this angle. Okay, okay, and you can see that it's pi by 2 plus this angle, and that angle is nothing but your tan inverse 1 by root 3, or you can say tan inverse b by a, which is root 3 by 1, you can say. You can say in this way. When looking at this angle is, this is root 3 and this is 1, the distance, I mean that is 1 distance wise. So root 3 by 1, so this is pi by 2 plus pi by 3, so you can say 5 pi by 6. Okay, so this is how different complex numbers, so 2 was represented here, 1 plus I was represented here, I is represented in this way, minus 3 plus root I is represented in this way. So different complex numbers can be represented and we have calculated modulus and complex numbers of them. Modulus is the argument of them. So let's now see the polar representation of complex number. Okay, so given the modulus r is equal to mod w, and let's write down, given the modulus r is basically mod w, where w is the complex number, and argument theta is basically argument of w of a complex number w, which is a plus ib, then we have a is r cos theta and b as r sin. So this you can just readily observe from the graph. I mean, if you have something like this, if this is represented a plus ib, okay, and this is theta, so obviously this is r cos theta and this is r sin theta. Okay, okay. So this is your real axis and imaginary axis. Okay, so the polar representation is basically nothing but writing a and b in terms of r and theta. So it becomes r cos theta plus I r sin theta. Okay, so this is basically the polar representation, or to just you can write in this way also, cos theta plus I sin theta. Okay, so this together form is called polar representation of w. Basically writing in terms of r and theta, writing in terms of modulus and argument. If you write a complex number in terms of modulus and argument, that becomes the polar representation of that complex number. Okay, polar representation of complex number. Now coming to another important definition, which is conjugate, not conjugator, conjugate. Okay, so complex conjugate of a complex number is another complex number w bar, and that w bar is basically defined as like this, a minus ib. Okay, so what it physically means, let's see. So what it typically means is that in the argand plane, let's plot, you have something called a plus ib, and this is the point which represents a plus ib. Okay, and if you join that, okay, so this is the real axis, this is the imaginary axis. Okay, and this is how you join. Okay, so the important thing here is, how does a minus ib look like? A minus ib is the complex conjugate of a plus ib. So the real part is same, okay, and only the imaginary part has come down. The imaginary part is negative minus b. So this is how the complex conjugate looks like. Okay, on the real ordinate, the real coordinate is same a, but the abscissa is same, the ordinate has come down. Okay, so basically it is symmetric, or it's a mirror about the real axis. That's what I can say. It's basically reflection of w about the real axis. Okay, that is what is your complex conjugate. Okay, now always we write in this way, 2 plus 3i, that becomes 2 minus 3i. Similarly, complex conjugate of 3 is basically 3, because the real, I mean, if you reflect about real axis, it will be same thing. And similarly 2i, if you just reflect it, it will become minus 2i about the axis. Okay, so the real part of the complex conjugate is same as the real part of the actual complex number, whereas the imaginary part of complex conjugate is negative or minus of the imaginary part of actual w. Remember, this is minus of im of w. Okay, and whereas the modulus is same, both has same modulus, the distance is same, and the argument is reversed. I mean, this is the argument measured in the counterclockwise. If this is theta, then obviously this is minus theta. Okay, so argument of w bar is basically minus of argument of w. Okay, so we have seen the real part remains same, the imaginary part gets multiplied with minus, basically the ordinate has come down, modulus remains same, the argument has is different, the argument becomes the negative. Okay, so these are what is a complex number and what is a complex conjugate. Okay, so this was a discussion about complex number and its complex conjugate. Okay, so now let's see various arithmetic, complex arithmetic, or the addition, subtraction, and all that is different. So we'll not go much into the detail, but what does multiplication means in terms of graphs? I mean, that's the idea. So only thing is the addition and subtraction, okay, is similar to the real numbers. Okay, say for example you have sum and the differences. Let's see how sum and differences of these numbers are done. Okay, so if you have w as a plus ib and z as x plus ib, okay, so w plus z will be basically a plus x. Okay, this is the real part, and the imaginary part will be b plus y. So this is how it is written. And w minus z is basically subtracting the real part, and then okay, so this is how it is done. Okay, so more or less it's similar to your real numbers. Okay, so just you have to treat as if it's a real number and then just multiply. Okay, and now multiply. So all the properties like commutative, addition is commutative, associative, all those properties hold here. Okay, now multiplication is similar to real numbers. So let's see what happens. So say for example you have 2 plus 3i and you have 1 minus 2i, so you have to just multiply. It's like x plus a plus b into x plus a. How do you, I mean, how do you multiply? So it will be like 2 into 1 2, then minus 4i plus 3i, and then it will be minus 6i square. Now I square you have to represent it as minus 1, so it will be 2 minus I plus 1, because I square is minus 1, so it is 8 minus I. So this is how multiplication is done. Okay, so it is similar to your just similar to your real number. Okay, so let's see how does multiplication looks like in argand plane. So if you have w and z, two complex numbers, then the modulus of the product will be basically mod wz, which is nothing but mod w into mod z. Okay, and the argument of the product of these two numbers would be argument of wz, which is nothing but argument of w plus argument of z. Okay, so just to prove this, we can just take w to be a plus ib, or in fact we can just take the modulus argument form, which is r cos theta plus I sin theta. Similarly, z as x plus iy, and let's call s is the model. So r here is root over a square plus b square, and theta is tan inverse b by a. Similarly, s cos, let's call phi I sin phi, where s is basically root over x square plus y square, and phi is tan inverse b by a. Tan inverse, sorry, y by x. Y by x. Okay, so this is how w and z. Now the product will be basically w z. If you just multiply, it will be r into s cos theta plus I sin theta into cos phi plus I sin phi. So if you just multiply these two together, you will get cos theta cos phi plus I sin phi cos theta plus I sin theta cos phi, and then minus I square plus I square sin theta sin phi sin theta sin phi. So this becomes rs cos theta cos phi. Okay, cos theta cos phi, and this I square is minus, so I square I can write, so minus sin theta sin phi, and I can write, I can easily write sin phi cos theta plus sin theta cos phi. Now here I need to use the trigonometry identity. So this is nothing but cos theta plus phi. Just expand, you will get. Whereas this is nothing but sin theta plus phi. Okay, so this is like modulus rs, and argument is basically theta plus phi. So this is basically the product. This product can be represented in this way: modulus rs and theta plus phi. Okay, so what happens in a plane? If we have, say, w is here making angle theta, z is somewhere here making angle, this angle is phi. Okay, so wz will be, the modulus will be somewhere here. Let me just represent it correctly, or not, let me draw it correctly. So this is something like this, this is something like this. Okay, so what it means is, if I have z in this way, oh sorry, w in this way representing angle theta, and say z is in this way representing angle phi. Again the graph has not come. Okay, let me cancel it. Last time it has not come properly. I just wanted to represent how it looks like. So this is how the z is there, this is how, so let me call this as z and this as w. So now what it says is, your w is, I mean the wz is something like this, where the modulus is multiplied, and the angle, they say this is theta and this is phi. So this angle together, this angle will be theta plus phi. That's what the argument says. Okay, and the modulus is multiplied. So just a small representation. Okay, and now multiplication of a complex number by I, complex number by I. So let's represent what happens, multiply a complex number by I. So basically mod ij, we know the product, the product is basically, if you have z and I, two complex numbers, so product, we can write modulus to, in order to find out the product modulus, it is something like this: modulus of I is 1, so modulus of z is z. So when you multiply with I, the modulus remains same. Now the argument of ij is nothing but argument of I plus argument of z. Argument of I is pi by 2 plus argument of z. So what we see is modulus is same, only the argument has increased by pi by 2. So what happens is, if you have w like this, okay, then if you have, sorry, z like this, let me call z here because we have taken the example z. So your iz will be somewhere here. Okay, this is iz. Okay, the modulus, this modulus is same. Only thing is, if it is theta, this angle should be pi by 2 plus theta. So intermediate angle has to be 90. Okay, so this angle is pi by 2 plus theta. So basically you can say the multiplication of z with I leaves the modulus of z unchanged, but it increases its argument by pi by 2. So it's about basically rotating rotating the position vector of z. So basically multiplying the complex number by I basically rotates the position vector z counterclockwise direction by 90 degrees about the origin. Okay, that's what the multiplication of a complex number by I does. Now let's come to an important theorem about complex number, De Moivre's theorem, which says that cos theta plus I sin theta whole power n is basically cos n theta plus I sin n theta. Okay, so let's do a quick proof of this. Z is say cos theta plus I sin theta. This is basically a polar representation form of complex number where modulus z is 1 and argument is theta. Okay, now if I have z power n, which is nothing but cos theta plus I sin theta whole power n, if I have, then the modulus of z power n, I mean the modulus of zn is modulus of zn, which is 1 power of n, which is 1. Okay, now argument of z power n will be argument of basically z n times, and that becomes basically argument of z plus argument of z, because addition arguments, the angle gets added up. Okay, so this is how it looks like. So it will be cos theta plus I sin theta. Okay, the argument is getting added. So argument of z is theta, this is theta n times, so this become n theta. So basically you have the modulus is 1 and the argument is n theta. So the new number you can write modulus as 1, argument is n, so cos n theta plus I sin n theta. Okay, so this is how the modulus looks like. Okay, so this is how the z power n looks like. So we started with this and proved this. Okay, so this is an important theorem which helps in simplifying complex numbers. Okay, so basically you can calculate the power of a complex number. So let's take some example. Express 1 plus I whole power 5 in a plus ib form. Okay, so 1 plus I whole power 5, the modulus is basically, or I mean if you can write this in the form of cos theta plus I sin theta, so let's do in that way. Okay, so cos theta plus sin theta. Okay, now the modulus of this, okay, the modulus of this will be basically root over 1 plus 1 is equal to root 2. Okay, so 1 plus I can always write cos pi by 4. Okay, Okay, I can always write cos pi by 4 plus I sin pi by 4. Okay, and means writing in terms of cos and sine. Okay, and this is 1 by root 2, and this is, so in this way I can always represent this number. So this number I can write 1 plus I in this form, root 2 into cos pi plus I sin pi. So where root 2 is the modulus and the argument is pi by 4. Okay, now I want 1 plus I whole power 5, that is basically root to the power of 5 plus cos pi by 4 plus I sin pi by 4 whole to the power of 5. Now I can use the De Moivre's theorem, which says cos theta plus I sin theta as, so root 2 power 5 will basically is 4 root 2, and this becomes cos 5 pi by 4 cos n theta plus I sin n theta, so I sin 5 pi by 4. So this will be basically 4 root 2 cos pi by 4 is minus root 2, basically it's 5 pi by 4, you can write as 2 pi plus, or you can write basically pi plus pi by 4. So 180 plus pi by 4 cos 180 plus pi by 4 is minus cos pi by 4, which is minus 1 by root 2, plus I sin pi by 4 is 180 plus pi by, so it's in third quadrant, so both sin and cos are negative. Okay, so this you can simplify as minus 4 minus 4i. Okay, so this is how the power of easily, so always you have to express the complex number in this form. Okay, r cos theta plus I sin theta form, and then it's just using the De Moivre's theorem. Okay, so now what is given is simplify 2 plus 3i by 4 minus I. So we need to simplify this and express in a form. This you can, so this was a bit, and b bit is I by 1 plus I root 3. So we need to simplify this and express in a plus ib form. Okay, so let's take this 2 plus 3i 4 minus I. Now we can multiply with the complex conjugate throughout. Okay, so this will be 2 plus 3i into 4 plus I by 4 4 16 minus I square, which is I square is minus 1, so this is 17. So this is 2 fours 8 plus 2i plus 3 fours 12i plus I square and plus 3i square. So this will be 8 plus 14i minus 3 by 17. So this becomes 5 plus 14i by 17. So this is 5 by 17 plus 14 by 17i. Okay, this is what is the first. Now b, this is for the first bit. Now second bit is something like this. Now we need to multiply, and we need to multiply with the complex conjugate, so this will be 1 minus I root 3 in order to make the denominator to be a real number. Okay, so this will be I minus I square root 3 by 1 square minus I root 3 whole square. So this will be I minus I square is 1, so I square is minus 1, so it become 1 plus I plus root 3, and this is 1 minus I square into 3. I square is minus 1, so this becomes 4 I plus root 3. So this becomes root 3 by 4 plus I by 4. So this is the another form of simplified form of I plus 4. Okay, so now let's see roots of a complex number. Roots of complex number. Okay, something like we had x square is equal to a, then it says plus or minus root a. So this is for real numbers. So similarly, if w square and square of a complex number is another complex number, so w can be written as plus or minus root z. Okay, whereas w is equal to root z is called the principal square root of z. Okay, So if z is r cos theta plus I sin theta, okay, then the complex number w is denoted as root r cos theta, and cos theta plus I sin theta whole power 1 by 2, which is written as cos. This is another extension of De Moivre's theorem. For De Moivre's theorem uh, can be applied when for n, whether it's integer or n is a rational number. Okay, so this is another extension of. I don't think that it's applicable only for integers. Okay, because this will clearly, because this, if you have w something like this, okay, just think from the back. If you have w something like this, I mean, it's not, I mean, you have to think in this way. If I assume, let's not write in this way. If I assume w to be this will satisfy w square to be r cos theta plus I sin theta, because if you just, okay, so basically it satisfies this, because if you square this, okay, and use the De Moivre's theorem, you have to come in this way. Okay, so this becomes the principal root of a complex number. Okay, just to simplify ideas, let's take some examples. Say root 4, I can always, it's better to represent in polar form, so I can write cos 0 plus I sin 0, right? Okay, and root, so it will be root 4 plus cos 0 by 2 plus I sin 0 by 2, so that will be anyhow 2. Okay, similarly root I is what? So I can write modulus as 1 cos 0 plus I sin pi by 2. I can write cos pi by 2 and I sin pi by 2. Okay, cos pi by 2 is 0, so I can write I sin pi by 2. Now because of the root, it will be cos pi by 4 plus I sin pi by 4. Okay, so it is basically 1 by root 2 plus I by root 2. 1 plus I by root 2. Okay, that is the, okay. Now minus root minus 4i. How do I write this? So root minus 4i, I can write 4 is the modulus. I mean, modulus can't be negative. Now in other sense, I can write this as cos minus pi by 2 plus I sin minus pi by 2, because if minus sin pi by 2 is minus 1 and cos pi by, minus pi by 2 is anyhow 0, so this will make root minus 4. So root 4 into, this will be cos minus half of this, so minus pi by 4 plus I sin minus pi by 4. So this will be 2. Okay, and this is cos pi by 4 is 1 by root 2 minus I by root 2. Okay, so this I'm just writing out here. This will become root 2 minus I root 2. Okay, this is the square root of minus root minus 4i. Okay, so similarly, let's have another square root, which is minus half plus I root 3 by 2. Well, the idea is basically to represent this number in the available form. Okay, so now cos theta is minus half and sin theta is root 3 by 2. So cos theta is negative, sin theta is positive. So this can happen in the second quadrant. It can happen because second quadrant cos is negative, sin is positive. So theta, if I assume, I mean theta will be what? Theta is basically sin theta is root 3 by 2. So if I assume theta to be pi by 2 plus 60, okay, so will I get, well, sin theta root 3 by 2. So you can actually try to find out this. I mean half, if I put 30 sin, yeah, I think pi by 2 plus 60 should do the trick. So I think pi by 2 plus 30 will do the trick, because pi by 2 plus 30 is basically 2 pi by 3 or 120. Okay, so cos 120 is basically cos 90 plus 30, which is because of 90 sign will change, so sine, and it is negative in the third corner, so minus sine 30 is minus half. Similarly, sine 120 is basically sine of 90 plus 30, which is cos 30 with a plus sign because sine is positive, so cos 30 is root 3 by 2. It's basically sine 60, which is root 3 by 2. Okay, so basically the angle is 120, so I can express minus half plus I root 3 by 2 as cos, because the modulus is 1. I mean, you can always look at the modulus. Modulus of minus I plus root 3 by 2 is basically r, which is nothing but 1 by 2 whole square plus root 3 by 2 whole square. So this is half plus 3 by 4. 1 by 4 plus 3 by, which is 1. So basically the modulus is 1, so I can express this in cos theta plus I sin theta form, or cos 2 pi by 3 plus I sin 2 pi by 3. Okay, so therefore now minus half plus I root 3 by 2 is basically r cos theta by 2 plus I root r sin theta by 2, right? Okay, so root r is 1. Okay, cos 2 pi by 3, half of that is pi by 3 plus sine pi by 3. So this is basically cos 60, which is half, and sine 60 is root 3 by 2. Okay, so the root of minus half plus I root 3 is basically half plus I root 3. Okay, so in general, if there's a statement coming here, if z is a non-zero complex number and theta is principal argument means without taking, I mean taking theta, restricting theta to be in the interval minus pi to pi, so theta is the principal argument of z, that is theta lying here, then the nth root of z can be written in this way: modulus 1 by n cos theta by n plus I sin theta by n. Okay, so till now, before this we saw just the square root, but in general the nth root of a complex number can be written in this way, where this is called the principal nth root of z. Okay, this is called the principal nth root of z. So this is the general. So we have seen the square root, and this is the nth root of z. So this was all about reviewing whatever we are supposed to know in complex numbers. We have seen what is starting from what is imaginary unit I. First we have seen why we need complex numbers. Then we have seen what is imaginary unit I and how to express complex numbers. What is modulus? What is argument? And then we have seen how to represent complex numbers in argand plane, basically in coordinate plane, where each term x comma y represents x plus iy. And then in terms of the argand plane, what is argument, what is modulus? Modulus is the distance between the origin to the complex number. Argument is the angle measured in counterclockwise direction from the x-axis or from the real axis. Then we have seen what is real axis, what is imaginary axis, and then we have seen how to multiply, how to add, I mean basically the complex arithmetic part. But before that we have seen what is complex conjugate. Okay, and then what happens in addition, what happens in multiplication. Important point in multiplication is that when you multiply a complex number with imaginary unit I, it gets rotated by 90, portion vector gets rotated by 90. And then we have seen how to simplify complex numbers. We have seen De Moivre's theorem, which is a very important theorem. And then we have seen roots of complex number, basically the square root, and now the nth root of a complex number. So now after learning what is a complex number and basic, now we have some basic knowledge of complex numbers. So let's now see functions of complex numbers. So functions of complex numbers means you may have function of x. Let's say something 3x square plus 2 is basically a function of x. So similarly, like I can have 3z square plus 2, or something like log x, I can have log z. E power x, I can have e power z. So all that, let's go to next section, which is complex